Oh, hello students. Welcome back to today's lab. Today we're going to be learning about optical instruments, which is basically taking what we learned last week about what individual optics do on their own and putting them together to form actually useful tools with them. The probably simplest optical instrument we're going to talk about today is the magnifying glass. The magnifying glass is just a simple converging lens which takes light from a point at its focus point and makes that light parallel in a bigger area, and that way your eye can actually observe it. So your eye is probably not the simplest optical instrument. It's actually a very complicated optical instrument, but it is the most well known. So between these two we form an optical system which can magnify very small objects so that your eye can make sense of them. So again, a very small object shines. A lens is placed so that that object is at its focal point. The light comes out, and since it's at the focal point, it continues on parallel to the horizontal axis of your eye. A lens in your eyeball, shown over here, then refracts the light to a focus point in the back of your eye where there's lots of receptors, and your brain can make sense of what these receptors are seeing and make that into a picture in your mind. So your eye can see light that is coming in parallel to its horizontal axis very well. So this is seen whenever we see faraway objects, stars, or even things just a meter or two away. The other way our eye can make sense of things is if it is at or within the focus point of our eye. So our eye's focus point is around 25 centimeters away from the front of our face. So you'll notice when you're reading, there's a very comfortable reading distance, which is where you will normally place things you're trying to read. And that's about 25 centimeters, and it does change from person to person depending on lots of different variables. Your eye can adjust using muscles, which changes the shape of that lens, which can still reflect and refract the light to a focus point in the back of your eye. And this is if everything is working correctly. If you have some sort of eye condition, nearsightedness or farsightedness, this focus point will either be in the middle of your eye, or it will be behind the back of your eye, and that's where corrective optics or glasses will come in. Basically, they change the light out in front of your eye so that when the light comes in, whatever your lens is doing will refract the light to the focus point on the back of your eye. The muscles in your eye can also accommodate for things not exactly at the optimum viewing distance. So if it's a bit further away, you can still read things using your very close vision. And if things are closer, you can still look at them to a point. There is a point when you move things close to your eye where you won't really be able to resolve what that object is anymore. So the eye is a very complicated thing, so there's much more we could go into. We could spend classes and classes just talking about the eye. But for today, we will just know that the eye exists and that the eye can view things coming from a focus point or coming in parallelized light. Back to our magnifying glass, putting in the 25 centimeter viewing distance for our eyeballs, which we prefer to be at, the focal length of our magnifying glass can be thrown in this equation here, which will give the magnification of an eyeball and magnifying glass system. So shown here, m equals 25 centimeters over the focal length plus 1. So that is probably the simplest system we'll be working with, and it can be very useful, but it does have its limits in research, especially as things get smaller and smaller. Which is where the compound microscope comes in. Compound microscope is using two converging lenses basically to take something very, very small and make it bigger so that we can view it from the other end of the microscope. So the later instruments, the optical microscope and the telescopes we'll talk about in a minute, are made up of two lenses. You can make more and more complicated versions of this with really any number of lenses that you want, or even mirrors. But the simplest versions of these will all be two lens systems. These two lenses are the objective and the eyepiece. The objective, very simply, is the lens closest to the object you're viewing. So on a microscope, it is the lens right next to your specimen, and the eyepiece is closest to your eye. So what you put your eyes on an actual microscope is the eyepiece. By changing these two lenses, we can change the magnification and the clarity and make things fit in the systems we're looking at. So there are reasons to have less powerful microscopes, more powerful microscopes, as well as telescopes of different specifications. So in the compound microscope, our objective lens is a converging lens, as well as our eyepiece is also a converging lens. So this converging lens, its focal point is here. Its other focal point is about here, and the specimen is a bit further away than that focal point. Between the two lenses, there is a distance of the objective focal length plus L. L is known as the tube length, and is just a separation between the focal points of our lenses. And then our eyepiece is another converging lens placed L plus FO plus FE away from the first lens. And then over here is your eye. And looking at the ray diagram of what the light does, it goes through the first lens, it's refracted to a point where a real image is formed. Real image because there is light passing through that point. This light continues on until it goes through the second lens. And the second lens treats this real image like an object. It treats it like its object, but it doesn't see it as an actual object because there's nothing there. It's just the light coming to a focus point here. However, it does bend that light just as you'd expect, and when your eye sees these bent light rays, it backtraces them to a virtual image, again, not formed by any actual light rays coming from that point, which is bigger than the specimen or the real image, being the largest of the three images formed. So this is why your eye can see something appear very large, that would be very small to begin with, slightly bigger if we were just using one magnifying glass basically, and then to a large point. And by changing around our optics, we can tailor this to be about as big as we want within reason. So finding the magnification of our compound microscope is as easy as multiplying the magnification of the eyepiece times the magnification of the objective. Eyepiece is just, again, your eye over the focal length of the eyepiece. And the MO is a bit different. We need to put the tube length in there and the focal length of the objective lens. The tube length, 16 centimeters, is a standard by the Royal Microscope Society. There's probably a good reason for that, but it can change. There's no real background given in today's class as to why that is 16 centimeters. But we use that, we can put it all together to get this equation here to find our magnification and how we could get greater magnification values by changing our objective, eyepiece, or tube length. All right, and the second and last part of our lab is working with telescopes. So there's two different types of telescopes: refracting telescopes, which use lenses to bend the light, and reflecting telescopes, which use mirrors. Both of these telescopes work in pretty much the same way. Just with mirrors, all the light stays on one side, and with lenses, the light is passing through the lenses. Today we're going to only be working with refracting telescopes, but you could very easily substitute in mirrors for things like this, remembering that light will be bounced back in the direction it came from. Just like with the microscope, we have an objective lens and an eyepiece for both the telescopes we'll be working with. The Galilean telescope, the objective is a converging lens and the eyepiece is a diverging lens. They're spaced apart so that the focal points align on top of each other, meaning that the eyepiece is to the left or on the light coming inside of the focal length. This means that the light being directed from very far away, all coming in parallel to the horizontal axis, is pointed at this focal point, but since the diverging lens is there, it will enter the eye all parallel to the horizontal axis. With any telescope, you want your objective lens to be as big as possible. This is for a few reasons. The main one being to gather as much light as possible. So you are taking a very, very small image and making it bigger. If there's not a lot of light coming from that image, such as from stars or planets, other than the sun, you will lose a lot of the light as you expand it. So you want as much light gathered by this as possible. You also want to have certain length for focal points, because the magnification is tied to the focal lengths of the objective and the eyepiece. So negative the length of the focal point of the objective over the focal length of the eyepiece. You can see from this equation here which variables you would want to change to have the largest magnification possible. So you can either change the eyepiece or the objective to get to the largest magnification, or any magnification that you want. And then the tube length, or the length of the telescope tube, is given just by the distance between the two eyepieces, or adding up the two focal lengths. So using this is known as the Galilean telescope, a converging lens, and a diverging lens. The other type of telescope we'll be working with today uses two converging lenses. Again, they're aligned so that their focal points are on top of one another, with the objective having a long focal point and then the eyepiece being to the right of this focal point, but still aligning. This means that any light coming from this focal point and going through the eyepiece will be directed parallel into your eye, so your eye can make sense of the image that forms. Again, light is coming in perfectly parallel to the horizontal axis because we're looking at a very far away object, so all of the light is parallel. And we can again arrive at what our magnification value is using this equation here and changing the eyepiece and the objective lens. Alright, so talking about the eyeball, trying to get a perspective of what's going on, we're again working with our laser ray box simulating light coming in parallel to the horizontal axis of our eye. And this is similar to what we would see looking at objects at really any distance greater than 25 centimeters or a meter, or any larger than that. Faraway stars, trees, even people that you aren't sitting super close to. So when the light comes into the eye, it's already parallel, but the eye can't really make sense of that when it's all hitting the back in a parallel function. So the lens in our eye acts to refract the light to a focus point on the back of our eye, and that's where much of your optic receptors are. And they can change light into signals that go to the brain that can come together and create a picture of what's going on in your eye. And you want your focus point to be right on the back of your eye where all of these receptors are clumped. If you are nearsighted, you have a slightly different situation going on. So instead of all of the light hitting the very back of your eye, it is focusing to a point in front of the back of your eye, and the light that actually reaches your receptors is spread out, and that's why you see a blurry picture of the world around you. So the glasses that you have is a diverging lens, which basically just spreads out the light a bit more, changes the focal points, and that should allow the light to focus to the point on the back of your eye. So what we have here is a set of glasses, a diverging lens, along with a nearsighted lens, and they come together to, again, focus the light to where your eye wants it to be. Farsighted people have the opposite problem. The lens in their eye focuses the light behind the back of the wall. So again, all of the light hitting the back of the eye wall is a bit more spread out than focused to a point. So you again see a blurry image. To fix that, there is a converging lens, which when placed in front of the eye and aligned, you again get the focus point of the light at the very back of your eye. So what you want is this situation here. Pretty much all vision is seen this way, further away than the near point vision that we discussed earlier. Alright, so using the simple magnifier method, we're going to find the focal length of each of our converging lenses. So this is lens 1. We're just going to move it towards the screen while the other end is pointed out the window until we get the sharpest image. And then make the recording at that image, so 5.5 centimeters. We're also going to repeat this with another lens. This lens has a much longer focal length, but it should work the same way. So we can see the trees forming their image here. That's too far, and this is a bit subjective, so these results may not be perfect, but that right there looks pretty good. So 68.5 centimeters. And then our third one is the one we used last week, so we already know that. And then our fourth lens is the diverging lens. We had to use a different method to do that, but we also got a number for that, which will be on the handout you receive online. Alright, since it doesn't really take much time, we're just going to show you how you measure the focal length of a diverging lens. So I have my lasers set up here with a converging lens in the light path. All the light converges to a point here, so I'll mark that point. And then putting my diverging lens in the light path, one thing we know is when the focal point of this aligns with the focal length of this lens here, we should get parallel light. So I'm just going to move it backwards until the light coming out of this appears to be parallel. And again, this is a bit subjective, but we've done it a few times to average out the results and then make a mark there. And then measuring between these two marks, we will get the focal distance of our diverging lens. So it's about 9 point something centimeters. That'll go into our average, keeping in mind that this will be a negative value when it shows up on your sheet. Alright, so here we have our compound microscope set up. We have our arrow-faced lamp first on our optics table, and then one of our smallest focal lengths away, we have our lens with the smallest focal length. After that is a length that is made up by this first lens's focal length plus 16 centimeters plus the focal length of the second lens, which is lens 2. Then after that, we have moved our screen to wherever we can find the best focus. And now we're going to measure this focal length. We measured it a moment ago and it was about 1.5 times as large as the object on the lamp. The next thing that happens is the instructions tell you to look for the maximum practical tube length. And basically what we want to do at this point is move everything except the lamp to find this maximum practical tube length. So the first thing we're going to move is this, which immediately puts everything out of focus. And then I will start moving my other optics. And we can see as I move everything in conjunction to one another, our image gets much, much bigger. So we'll move this a bit more to try to get the biggest image possible. The practical part of this is both determined by how long our optics table is, as well as how much dimmer our image is getting as we move this down the table. So right about here I can still measure my image, and if I dial in the focus, I can get something that I can actually measure the magnification of. So knowing that each tick mark is about 1 millimeter, I'm going to measure it here. So the distance between the tick marks is about 1.2 centimeters. So our magnification is 1 millimeter to 12 millimeters with the maximum practical length. Alright, so here we have our Galilean telescope setup. We have our longest focal length objective optic on the end, and then our diverging lens eyepiece here. They're placed at a distance D apart, where D is just the two focal lengths added together. Some fine tuning's involved with moving this back and forth just to bring what we're looking at into focus, and then this camera here is going to record your view that you'll see basically if you had your eye here and you're looking out the window. What we're looking at is the library, hopefully that you're all familiar with from campus. Alright, so here we can see down the barrel of our setup. Notice that you can still see pretty much everything outside the lens, and the only place that's magnified to any real degree is through the second lens. This is why most telescopes have a barrel, so that you're not distracted by everything else around you. Right now I'm zooming in on the L from library. You can see it's much, much larger than what it would be. And at the end of this, hopefully you'll be able to see all of the letters and make a pretty good approximation about what the magnification actually is. There's the R, A, R, and the Y. And if I kind of move this to the side, you can see how big these things appear on the left side of your screen without using the telescope. Alright, here is the Keplerian telescope. It's a bit harder to line up, but I have lined it up with the sun on whatever that new building is called. There's the edge. Follow that edge. There's an orange bit. We're going to go downwards on that orange bit. See the tip. Around there. We are now looking out the north side of the building, south engineering. Alright, so this is kind of an overview of it. As it gets brighter, it's a bit hard to see. But that is the sun, and we'll show you a view of the sun through a normal optic in just a second. Alright, this is the view just from the camera itself. You can see the sun on the corner of that building, viewing it through a screen, so it's a bit harder. One thing that didn't come through great in the last video is that the sun did appear upside down, so make sure that works its way into your worksheets. That the sun did appear upside down, but we can at least get a view here to see about what the difference is between the magnified version and the regular version.